Thanks so much. Appreciate it. So as he mentioned, Jacques, it's nice to meet all of you. I've got really two hats, and I'm sort of moved between the two different hats in this talk. So one of my hats is that I'm co-founder and CTO at Dremio, and the other is that I am the PMC chair of Apache Arrow. And so I'll be talking a lot about Apache Arrow, what it means, how it can make things go faster, but also give you some context in terms of how we use it at Dremio to build our technologies. So quickly I'll go through the background on Arrow and sort of how it came about. I'll then talk about the components of Arrow. I'll talk about sort of the basic data structure, which is the Arrow data structure, so you get a little bit of sort of that in your head. And then I'm going to go in and talk about Arrow specifically for query processing and how we've found different techniques to make it perform very well for processing purposes. And so that'll be hopefully a quick 25 minutes or so. So to start with, most of you have probably heard of Arrow by now, I hope. It is a standard for columnar in-memory analytics, processing, and transport. Okay? And so it is focused on many different workloads, trying to speed up those workloads, designed to allow you to have a common data layer between different components. It's designed to work with any programming language that you want it to work with, and there are quite a few that it supports already. One of its core tenets is this Apache Foundation project. And so an Apache Foundation project at its core protects you from being locked into any particular vendor or anything like that, and is driven entirely as a consensus-driven project. So where did Arrow come from? Well, it came from a collaboration between myself and Wes McKinney. We were talking about different problems we were dealing with in data. If you don't know Wes McKinney, he created Pandas. He wrote the most popular O'Reilly book ever. A brilliant guy. And we were chatting about sort of data problems in both data science and in data processing databases. And really, we kind of came to a shared conclusion. And the conclusion is that one of the big challenges when you're building a data system, and what I mean by data system is like what a company needs, not what one particular piece of software provides, right? Because generally speaking, when people are working with data, they need lots of different technologies, and they need to be able to bring those together to solve actual data problems. And one of the things that happens is it becomes very expensive to move data from one system to another, okay? And so typically, you'll try to do as much in one system as possible before you go to another system, because the boundaries between systems are expensive to move through. And so we started looking at that problem and said, you know what, we need to figure out a way to solve this. And so this kind of started out as a challenge around transport. It's like, how do I move data efficiently between systems? And so there's actually lots of transport approaches to data already. Like I could use REST and JSON. I could use protobuf or Thrift or something like that to move data between systems. But what we started to identify is that the core problem with all of those existing ways of moving data between systems is that it was expensive to move from what the internal representation of data was in each data system to what they could put on the wire and then communicate to another system. And there was different reasons for the expense. One was a transformation of the data in memory into a format that could be more appropriately sent on the wire. Another thing that was a problem is that most of the ways that you expose data was through APIs. And so if you wanted to interact with a particular amount of data, you actually have to call some set of APIs in whatever language you're working in to access it cell by cell. And so it basically means if I want to read 10 records and I read 10 columns in each record, I've got to do 100 method invocations just to read that data, right? And that was kind of the pattern with everything that was out there. And so we came to the conclusion that the way to solve transport, and so this sort of serialization, deserialization boundary, was to actually solve processing first. The idea being that if you start to use a common format inside of your processing engines, then when you decide to move from one processing engine to another, you don't actually have to change the format. You can take that format, you can drop it on the wire, hand it to the other system, and actually let that system process it as well. And so really this concept was, hey, in order to solve transport, you actually need to solve processing. And so Arrow was designed as a processing first representation of data that also is well designed to be able to transport between different systems. And so it's kind of this chicken and egg thing about how we got to the idea of Arrow in the first place. And so Arrow has done really, really well. So Arrow started about 4 years ago. 3.5 years ago, something like that. I don't know exactly. And we've seen huge amounts of downloads at this point, lots of different technologies adopting it. And so I think that it's here to stay. I think we hit past 4 million downloads a month about a month or two ago. So very happy with all the different technologies that have adopted it. So I'm going to do one slide about Dremio because that's people who pay my paycheck. And so quickly, we built a technology on top of Arrow called Dremio, which is a data lake engine. We describe it as a processing and semantic layer to interact with data wherever it might be stored. And it's all built on top of Arrow. Everything that I'm talking about in terms of the technologies here, we use those things at hundreds of customers running on thousands of nodes. So they're all things that you can trust as production-ready stuff. So I added one slide to my talk because I was listening to Thomas's talk just before this talk. So those of you that were here with Thomas's talk from Salesforce, I actually am very passionate about what he talked about, which is a table format. And so one of the big missing pieces, I think, in data lakes traditionally has been a table format, a common table format that can be used across many different systems. There are actually several different technologies that are in play there. And we actually have also come to the exact same conclusion that Thomas did, which is that Iceberg is the right one to follow. And so I strongly recommend to each of you, if you haven't thought about deciding on what table format you have and sort of focusing on investing in that, you'll probably pick one of the others. And I'm going to caution everybody that there's a path for all of the others that's taking you down a path that is going to feel more and more like lock-in. Because most of the other technologies are beholden to a small number of companies or a small set of technologies and not really designed to be consensus-driven to work with a large set of technologies. And that's my opinion, but it's something that I strongly suggest that you look at if you're thinking about how to do tables, and if you're not thinking about it, you should probably think about it. Anyway, that's sort of off topic, but it was something that came up when Thomas was talking, so I wanted to bring that up. So let's drop back into Arrow. So what are the components of Arrow? Well, the number one component is that it's an in-memory representation, but like memory by itself is not something that people can work with. People want to program against APIs. And so in addition to that, there are actually I think over a dozen now. I have some of them here, but I believe that there's over a dozen different language bindings for Arrow representations. So each different language binding figures out the optimal way to interact with the Arrow in-memory representation of data that is best for that language, right? And so one of the keys of the Arrow representation is that you never have to call into another language in order to interact with data representations. You can always use whatever is appropriately native to that language. So on top of that, there are lots of different, what I describe as building blocks. So first you've got the memory format, and then on top of that you've got sort of bindings for different languages, and then you've got these what I call building blocks, okay? And so this is 4 examples. There are multiple other examples of building blocks that are inside the Arrow project or near the Arrow project, okay? One is Gandiva, and I'll talk more about this, but it's an LLVM-based just-in-time compiler for expression evaluation. Another one is Feather, which is an on-disk format for ephemeral data movement between 2 different applications. Arrow Flight, I'll talk about that as well. An RPC protocol for moving the Arrow data between different systems. And Parquet, which you probably all know of. We've actually done a huge amount of investment to make Parquet and Arrow work really well together. And just to note quickly there, one of the important things to understand is Arrow is an in-memory representation, Parquet is an on-disk representation. So they don't compete at all. They're actually very, very complementary. And they both have similar concepts in that they benefit from using a Columnar representation, but the Columnar representations, while complementary, are not the same. And then on top of different building blocks, there are lots of different integrations that people have built on top of Arrow to use for their own purposes, right? So Pandas is actually using it to move data between a bunch of different types of processes. Spark is using it to move between Python and Pandas and Spark. I don't think it's enabled by default, but if you turn it on, it makes things like 50 or 70 times faster if you're using those kinds of operations. Dremio, as I mentioned, is we built what we call our Sabo engine entirely on top of Arrow. And then NVIDIA actually, they have their Rapids initiative and the CUDA data frame. And that initiative is actually all built on top of the Arrow representation as well. So it's not just about CPUs, it's also about GPUs. So if you want a high performance representation of data for processing purposes, this is the one that you want. Okay? Now, before we go any further, one of the things I think is really important to cover is what is Arrow and what isn't Arrow. Okay? So people kind of hear the words and they hear a lot of different ways that Arrow could be used, but I want to make sure that people understand what it is. At its core, it's a specification for how you're going to have data in memory. It's a specification for how that data is shared between different processes, and it's a set of libraries and tools and building blocks to work with that. Okay? It isn't an installable system. You can't go and say yum install or brew install. Well, you can say brew install Arrow for the development stuff, but you don't install something, you don't run a service. There's not an in-memory grid that is built that it provides. It's actually an internal tool for solving data processing problems. Okay? It's also not designed for streaming applications. It's designed for analytical applications where you're going to be moving large amounts of data. Okay? If you're moving one record at a time, it's not going to work well for you. So quickly, the structures around Arrow. Well, we describe it as a shredded, nested data structure. It's designed specifically to be randomly accessible, so you can get to any record without having to go over other data structures. And this is one of the key differentiations between Arrow in-memory data and something like Parquet on disk, which is not designed to be randomly accessible. Okay? When you're moving data between different systems, you're generally following this message pattern, where you basically negotiate schema between two different sets of processes or sets of parts of your application. You then communicate one or more dictionary batches, so Arrow does support dictionary encoding, and then you send what we describe as record batches, which is the batches of data that are in columnar representation that are typically not huge, so that you can pipeline between different parts of the system. They can be arbitrarily large, but generally for pipelining purposes, we don't make them that large. And how does the data actually lay out in memory? Well, it's pretty straightforward, it's pretty obvious, but it's designed in a couple of ways to make it really efficient for processing. And so let's imagine that we have some data on the left-hand side. We have an array of persons, and each person has a name, an age, and an array of phone numbers. Okay? That data represented in Arrow format is going to be what's shown here on the right-hand side, which is that you're going to first have a name vector. Okay? And a name vector or a name array has actually two substructures. The first is called the offset array, which tells you what the positions into the second data structure, the values array, actually points to. So the first record is going to look at offsets 0 and 1 and say the start is offset 0 and the end is offset 1. And that means that we're actually getting 0 to 3 is the first value for that string. So that's JOE. And then the second value will be start at the second offset in the offset array, which is going to be value 3. And then the third offset, which is going to be value 7. Okay? So 3 to 7 is actually the next value, right? Those are two completely independent memory data structures. And so, for example, if you wanted to process understanding the lengths of strings or be able to do a first level pass on a quality of strings by using length, you can interact only with the offset vector and never actually interact with the data vector. Okay? Age, let's say that that's a 4-byte integer. That's a very simple representation. It's basically an array of 4-byte integers end to end. Okay? Phone numbers is a list of strings. Okay? So it looks kind of like the string did in the first column, but you actually add an additional list offset to describe which elements in the individual string, which of the individual strings are in each list. Okay? And so the design of these things are all these sort of array-based data structures, and that allows you to do a bunch of interesting performance things, which I'll get into. So it also allows you to have a very clean way to pass data between different systems. Now, I didn't actually put it here for simplicity purposes, but every single structure inside of Arrow is also possible. It can be a null value or not an unknown value. Okay? And so in addition to these data structures, each of these things has a bitmap which describes whether or not each value is valid or invalid. Okay? And so when that data all gets laid out in memory, we've got that same data structure here. We actually compose this into a record batch. And so here we have columnar data. I've lost my cursor, so I won't use my cursor. But we have columnar data that describes basically the 3 structures for name that I just talked about, the 2 that I talked about plus the bitmap. We have the 2 structures for age. And then we have the 4 structures for phone numbers. Okay? And those are just all laid end to end in memory. You can do a gathering right onto the socket to communicate those things. And then you put a very, very small data header above it, which describes what the offsets, the lengths of each of these structures are. Okay? And so that's the amount of data that you need to be able to communicate between 2 different pieces of software, how this data works. Okay? And so if you think about that example I was talking about before, where you say I want to send 10 records with 10 columns from one process to another, I would have to run 100 method invocations. Well, in this case, I can hand this chunk of memory from one process to another process, and I have all 100 values without having to do more than like one method invocation, right? And so not only do I not have to do any work in terms of serializing or deserializing moving between systems, I also don't have to do a bunch of method invocations to get access to the data in the system that's receiving the data. So now that we have that data structure, let's talk about some ways that we can process that efficiently. So the first I'm going to talk about is a project called Gandiva. Okay? So Gandiva was something that we built at Dremio and open sourced and contributed to the Apache Arrow project. And it's designed really to be able to allow you to process Arrow, this memory representation of data, very, very efficiently. Okay? So if you get data into that in-memory representation, now you can start to do really interesting things with it. And so we have seen substantial performance improvements in our use of it and have it in a bunch of production use cases. So let's talk about what it is. So if you think about a data processing pipeline, you're basically taking data and moving it between 2 different points, right? And so in Arrow, when you're doing processing of Arrow, you're generally dealing with these Arrow record batches, and you're moving them through a pipeline, okay? And so the design of the Gandiva execution kernel is to be able to take an arrow batch and turn it into a new arrow batch. And that's specifically done to apply an expression tree against that. Okay, so a very simple expression tree might be A plus B. And so Gandiva understands the internal, the in-memory representation of arrow, and then optimizes the instructions that are designed so that you can take advantage of that representation. So if you normally wanted to interact with data, you would use something like a cell level interface, and you would call into that, and you couldn't take advantage of how that data is actually laid out in memory. Because the data in arrow is laid out in memory and aligned, that means that you can actually write the code for processing to take advantage of those properties. And so, as I mentioned, it's an expression library. It has, I think, hundreds or maybe even thousands of expressions now that you can apply against for different operations. Here's a couple of examples that you can do at the bottom here. And so let's talk about how it can make things faster, right? And so I talked before about you've got that validity bitmap, which tells you whether or not something is true or false. And then you've got the data itself that actually describes what the values are. And so if we use the example of A plus B, okay? When you're trying to actually do A plus B in a processing system, let's say a SQL system like Dremio, you actually have to do several operations. So first, you actually have to apply null semantics. So if A is B, then the output's actually B. I mean, sorry, the output's null. If B is null, then the output is null. Okay? So if either of those values is null, then the output is null. If they're both valid, then we do the operation. Okay? And so if you normally would do this processing, you would have a bunch of if statements to evaluate the validity of these values, and then you would then do the math if you needed to. Okay? The problem with that is it doesn't pipeline well on a CPU, because you're not going to necessarily be able to guess whether this is going to be each value is going to be valid or not valid. Okay? And so once you know the representation, and you know that the validity bitmaps are bitmaps, and you know that the data is stored independently, you all of a sudden can actually decompose this operation and do it in far less instructions. Okay? And so in this case, we can actually take the validity bitmaps and do a bitwise AND of those maps to determine what the validity of the output values are. And we can do that at the word size rather than at the individual record size, right? And so I can do 64 values at a time, do that and produce a new validity. I actually didn't do any if conditions at all to decide whether or not to do this operation. And then on the data side, I just always do the math. Okay? So again, while it potentially means I'm doing the math more often, I completely reduced all the other instructions that are happening, so it's actually substantially more efficient. Okay? And so we have these concepts of how we decompose all of these operations, because validity checking is actually a huge amount of expense in all this processing that we do. So that's one example of how it goes faster. Another is that we've lined up this data to be designed to work well on modern CPUs. And so one of the things that modern CPUs have is they have SIMD instructions, or single instruction multiple data. And that means that you can actually interact with multiple independent values simultaneously with a single instruction. And so here, let's say that I've got, you know, 4 2-byte values that I'm adding to 4 other 2-byte values. Okay? Normally I would do that each value at a time. But with SIMD instructions, I can say actually add all of these at once and then get a new result. Okay? And so on the if condition side, I've reduced a bunch of instructions. And then over here for addition, I've also reduced a bunch of instructions. And so these are different ways or techniques to get more processing, get more done on your CPU in less time once you have that representation and you know that representation well. There's a lot more to this, a lot more detail. You can go and look at it in the code, but that's kind of the high level on Gandiva. So how does it work? Well, basically, we defined a, again, language agnostic way to express what the expression tree is. So you can describe an expression tree using protobuf. Okay? So any language can describe this expression tree. And then you hand it to the Arrow library from whatever language you're in. It compiles it using LLVM at runtime to build the actual transformation logic. And then you have different language bindings to be able to push data through the Gandiva core. Okay? So you can basically, like, whether it's, and so we use it in Java. We also use it in C++. Other people use it in Python. There's Rust bindings, I think, now as well. So there are lots of different bindings to be able to push stuff through and process it efficiently. So how has it actually impacted us? Well, in a lot of cases, let's say a really simple expression tree, it's not that much difference, right? A lot of systems are actually pretty well optimized for simple expression trees. So, you know, 2 to 5x, something like that. But if you get to more complex expression trees, which frankly in the real world when you're working with customers that have giant, you know, 5,000 line SQL statements, you frequently see a huge amount of additional lift. And so I've got a benchmark link there, which is one of our customer scenarios where we applied Gandiva and saw a 70x improvement in real world performance. And so that's not going to be every use case, but it's a fairly powerful thing that we found useful. So that was Gandiva. Now there's a lot of other algorithms that you start to deal with once you're dealing with Arrow memory. I'm going to cover a couple of others. So the first is that when you're dealing with data, one of the key things to do is to be able to pipeline the system. So if one process is waiting for another process to do work because you're doing a lot of work in one process before you hand data over, then it's not a very efficient use of resources. And so frequently we're very focused on pipelining and moving data quickly down the pipeline so that the next thing, like shuffling it across the network or whatever, can be done as quickly as possible. And so generally speaking for us, we generally keep these record batches to 64K or less in size, the number of records that we have. And then we actually size it down based on how wide the records are. If you've got like a two-column record, well then you can probably have a pretty tall record batch. But if you have a very wide record with 500 columns, you're probably going to go narrower. And the reason is that you want to, generally speaking, keep the Arrow batches on your CPU's cache, and you want to be able to pipeline them through the system as quickly as possible. You do lose some efficiency when you're working on shorter vectors because you're going to have to hop out and hop back in more often. But the flip side is that you usually can benefit from pipelining and keeping those things not too big when you're sending them places. Second thing. So while Columnar is really good at working with the CPU, it actually is painful for some operations. So one of the operations that's kind of painful with Columnar is a filter. So in a traditional processing where you're working with row-wise representations, you'll just drop individual records as you don't need them, right? In a Columnar representation, you've got separate vectors for every value. And so if you want to drop a value, well then you'd have to recopy and compact all of those vectors. And so rather than doing that immediately, you actually apply a mask. Okay, we call it a selection vector, but you can think about it as just basically a set of pointers. Okay, and we size the pointer based on how much data we're going to have. And so we use frequently what we call selection vector 2, which is a 2-byte pointer that points into a record batch, which is why there's 64K or less, and tells us which records are valid in that record batch, so that we can mask it so that additional operations that might be doing copies themselves, like an aggregation or a join, we don't have to do an extra level of copying in between. And then a selection vector 4 is basically 2-byte pointer into a particular batch and 2 bytes into which batch you're actually interacting with. Okay, and we actually also have a 6-byte one that we use as well. And so trying to stay as compact as possible, but then solve those problems. Another interesting pattern that becomes a little bit challenging with columnar data is a parallel columnar shuffler. Let's say I want to shuffle data between, take it from one node and then hash partition it out to a bunch of other nodes. Okay? Normally you might do this again in a row-wise format. You'd apply the hash function, figure out the bucket, and then send it on its merry way. In a columnar format, you're probably going to do it a little bit differently, and we do it a little bit differently. And so first, what we do is we mux data so that we bring data together from multiple threads in the sending side so that we can kind of reduce the amount of buffering that we have to do before we send the data. And then we actually generate a bucket vector, which is a description of each value and where it should go. And then we go column by column over the bucket vector and the specific vector and make a copy of that, targeting each of the outgoing locations, pre-allocating all of the memory for those things. And so one of the common things you'll see with all of the columnar algorithms is a decomposition, so that you're working on, you may be reading the data more times, but you're interacting with a smaller scope of data in each operation. So once we have good processing, which is what we find with the Gandiva and these other algorithms, we then want to move the data. And so Arrow Flight is one of the newer components of Arrow, and it's this ability to move data between different systems. It's focused on bulk transfers for analytics purposes, and it's really sort of delivering on what we had as an idea 4 years ago, which is full interoperability of data between different systems using Arrow. Okay? So really simple concept. I want to send data between two different systems. A client and server can send data to each other. It can be initiated at either side. And basically it says, hey, I'm going to send some data. Here's the data. OK, I'm done. Right? Or hey, give me some data. OK, here's the description of the data. Here's all the data. And you're done. OK? So it's mostly effectively a peer-to-peer kind of protocol. But one of the key things it does is, so we're focused on analytical systems. We're focused on scale out. And so one of the key problems with the traditional communication mechanisms is they're typically single stream. And so Arrow has at its core the concept of multiple streams. And so you can go to a host that says, hey, here's all the different streams you can subscribe to for this data. And it says, here's 100 different what we call tickets. And so you need to consume all 100 tickets in order to get all of the data. And each of these tickets can be accessed on a subset of the nodes that are available in your cluster. And so you can actually go in parallel and have 100 nodes pull data from another 100 nodes using a parallel flight stream. So it's not just for single stream, although it works very, very well for single stream, but it's actually also designed for parallel stream. And so for example, inside of Dremio, we now have a connector that allows you to consume Dremio data in parallel into a Spark pipeline. So performance-wise, I've got a benchmark here. So we did a very simple example, which is accessing our tool Dremio. Dremio exposes ODBC and JDBC, and so we said, hey, let's go into a Python data frame. We want to load some data from an ODBC driver. Okay? We did that initially with PyODBC, which is what most people use, and we pulled 5 million records back. And in that situation, it took about 54 seconds. Okay? We then did the same thing. I did the talk with just the left and right side benchmarks, and someone said, hey, Turbo ODBC is way faster. You really shouldn't be using PyODBC as your benchmark. So we ran Turbo ODBC. It is way faster. It uses ODBC as the same thing. They've removed a bunch of Python code and replaced it with C++ code, and it takes 22 seconds. We then ran the exact same operation in PyArrow against the exact same system using the exact same stuff, and we got it back in 1.3 seconds. And so these times are all fine because I can sit there and wait in any of these cases. When you ramp this up to 1 billion records, it goes from something like, I think it's 2.5 hours to, you know, a few minutes. Something that you maybe go get a coffee and come back. And so it can really change the speed at which people can get to things. So where are we going from here? Well, the future is, we basically were building blocks up. So we started with community, we then introduced the format, we then started adding language bindings, we're continuing to add language bindings, then we did file format integrations for things like CSV and Parquet, then we introduced the Gandiva kernel for execution, then we introduced Arrow Flight for transport, and we're continuing down that path of adding more things to it, but most likely one of the systems you're using or a system that you're building should be using Arrow. So that's what I've got. I put up some links here of different things. So code examples, it's hard to show them here, so I just put them as links so you can go look at some of the things I was talking about in terms of algorithms. Feel free to try out Dremio. We've got an open source edition that you can download and play with, and go to GitHub and look at our code. That's some of the links here. Gandiva and flight benchmarks that I referenced are also linked here. So with that, thank you so much, and I got like maybe 1 or 2 minutes for questions.
So it looks like you have a lot of the building blocks to replace Spark and a variety of other processing frameworks. You know, if you had to say how you complement or could replace, or you know, how do you contrast with those types of frameworks versus a Dremio and its capabilities?
Yeah, so well, I think it breaks it into 2 different pieces because there's Arrow and there's Dremio, right? And Arrow is open source, and so the hope is that technologies, and that's already happened in many cases in Spark, adopt Arrow as a kernel to solve different things. So Dremio as a system, we are primarily focused on high concurrency BI. And that's kind of our sweet spot. So if you're trying to do a lot of analytics, trying to solve how you get to data, we solve more of that. Whereas we see people doing more data science workloads and ETL workloads on something like Spark. So if you were going to compare us to something, you'd probably compare us more to something like Presto or Snowflake. Got another question in the middle here.
Thank you. So one thing that I've sort of gathered over the past few years is one of the reasons why MapReduce sort of stalled is that it turns out that data movement is cheaper than people expected. Like, so it's okay to just spend 40 gigabits on like moving data between tasks. You mentioned RDMA very briefly. Do you find that in your experience in sort of production customers and larger deployments, are people actually, like, do they really need to shift the data, or is it okay, like, is there real adoption of like leaving the data in memory at, you know, the place that has custody of it and just accessing it remotely?
Yeah, so it's interesting. There's a couple different pieces in there. So I absolutely have the same observation that I think you have, which is that, so the big rise of Hadoop and the passion there was all around push your processing to your data, right? And that made a huge amount of sense when Google wrote the original paper and everybody was on a 10 megabit network connection. Now that everybody has 10 gigabit, 40 gigabit, 100 gigabit connections, it's not as much of an issue, especially since, I don't know, the vast majority of people are moving their large data lakes to the cloud, and there is no
no ability, or there's very little ability to be able to push any processing to that. And so generally speaking, I believe that people should stop worrying about pushing their data, their processing to the data, and just focus on solving their problems. Now, Arrow still fits very well in that because our passion is not necessarily to hold the data in memory all of the time, right? The question is, how do we optimize? So to give you sort of a very short, interesting thing, which is that everybody who reads Parquet in a production environment, whether it's Spark or Presto or Dremio or Impala, all of those tools actually built their own Parquet readers. And the reason that they did is because they had the same problem of basically reading and sucking everything through a straw of an API that wasn't that efficient for how they wanted to internally represent the data. Okay? And so what's happening with Arrow is that you now have a representation where people can pick how they want to write their APIs so that they are just focused on the data format. And so what we're starting to see is a consolidation of these things back into a single version of that code that's been written, and then different people can decide how to interact with the data once in a scenario format. And so I'll give you an example of that. As I mentioned earlier, we're very passionate about Iceberg. One of the things the Iceberg community is doing is now designing their system to be exposed as an Arrow representation, so any system that understands Arrow can consume that.
One thing that I've been working on a little bit in the past few years is stateful streaming. And I'm wondering if Gandiva has any support for state either within batches or between batches.
Right now, Gandiva doesn't have any support for state. It's designed to be an open framework, so people could add it, but it's not. Right now, it's a stateless system beyond the state of the expression itself. All right. Thanks, everybody. I'm happy to ask more questions.